yeah, I'm going to present this work on scaling. Should I? Ah, switch. Okay. Okay, yeah. So I'm going to talk about the scaling laws for amplitude surrogates, which I mean is a bit more on the theory side, but just to motivate it a little bit, of course. You know that scattering amplitudes are at the heart of Monte Carlo event generators, and calculating them it's quite expensive, especially when you go to higher orders. So the solution, the easiest solution, seems to be machine learning, using machine learning to predict scattering amplitudes, and they seem to be excellent interpreters for them. And here in this plot I borrowed from one of my colleagues. You see how the performance greatly increases and outperforms the classical interpolation methods by training in relatively small sample sizes of data. And well, here they show it for two different architectures of neural networks, the classical MLP and then Alligator that I'm going to mention briefly. But yeah, I mean, it's very cool that you get a very predictable increase in performance, and then, for reasons that will be clear, suddenly you get a plateau. So then it's kind of not as good, but the idea is, okay, let's understand this behavior, and okay, let's see how accurate we can get, and what's the price, how much training data, how much resources we need to invest. So to put a bit more context, very similar scaling behaviors have been observed in a lot of applications of deep learning. Here, in large language modeling, image classification, in shape classification in physics. And so the thing is, like, empirically, we see that performance increases predictably as a power law when you increase the training data set size, the computing resources, or the number of parameters, mainly. So you have a law like this, where X, Y, and Z could be any permutation of these three resources, and you get a law that's like this. So a constant, which doesn't mean much, the parameter you're scaling, so the exponent, which is just the slope you see in these log-log plots, and a constant, which is the plateau you see, which if everything else is well done and optimized, it should only depend on the other two parameters that you're not scaling, which suggests that, okay, if you see a plateau, it means that you're bottlenecked in one of the other parameters, so you should increase one of those instead of still increasing your scaling parameter that you're looking at. And so the theory behind this has been a bit behind, but there are a few people who suggest that there is a relation between this exponent and the intrinsic dimensionality of the data, which for things like large language modeling is maybe a bit ill-defined, but they do some things to estimate the dimensionality of their data. They see a correlation, but yeah, that's the context. So then we want to ask, okay, can we determine very general and universal scaling laws for scattering amplitude surrogates? And to do this, we will compare a lot of processes and see if we see this behavior. We'll do the scaling in number of parameters, compute, and data set size. We'll try different losses, and in particular, which is interesting for this conference, the heteroscedastic loss, which I don't think we heard it by name, but it's one loss. I mean, we've seen it 2 talks ago. I think that it's a loss that allows you to get systematic uncertainties. And, and of course also different architectures, as in the first plot I showed. And, but yeah, the thing is that if scaling laws are universal, we can reliably know beforehand how many resources we need to invest to get a desired performance, which is nice, because then if you don't, as long as you have an accuracy that is good enough that the error you're committing by using machine learning is low enough that you can ignore it, then you're fine, and you can generate way less data and have amplitude, scattering amplitudes for free. So, and as a bonus, because this is like very simple in the sense, like very theoretical, we know the degrees of freedom of our process. We're just looking at the Feynman diagrams of a process. So we know the degrees of freedom, and we can put to the test this relation between the scaling and the dimensionality of the problem, which will be nice to see. And okay, so let's talk about the data. So we have the 4 momentums of the particles in the process, and we want to go from there and predict the scattering amplitude of the process. We generated all the data sets using MathGraph, and all amplitudes at lowest order. There have been studies on higher order cases, and you see also scaling behaviors, but not that very systematic and wide search like this one. But yeah, the main case will be this QQ2TTH process, because it's particularly hard to calculate, and it scales surprisingly well with machine learning methods. So it's kind of the main focus. But then, okay, a lot of other processes that I'm not going to stop to mention them, but just to show that they span a very, very, very wide range of amplitudes. It's a wide range of amplitudes. And again, processes of different characteristics. So we have processes with massless particles, with massive particles. These ones with loops, with exchange of identical particles, without exchange of identical particles. I mean, many things, a wide range of processes. So it would be nice to see if these scaling behaviors are truly universal and apply to this wide range. Here, it's just like a histogram of the amplitude of the process in each one of these data sets, and the count. So it's a histogram of the amplitudes. But just to show that, okay, we have processes going from 10 to the minus 13 scattering amplitude up to that number that I don't know. I can see it from here, but just 10 to the 2. Okay. Okay, and just to quickly go through the setup of the neural networks. For the standard NLP, we reverses a bit the data. We don't use the raw 4 momentum of the particles. We calculate the invariance of the particles and use those as inputs. And that's why in the plus you will see MLP-I, because it's just referring to the fact that I'm using the invariance. And the amplitudes are log standardized, except for QQ2TTH, because on the first paper I showed that they didn't do it, so just to keep it comparable to them. Then, unless it's explicitly changed, and it should be clear when it's changed, the base model is like 500 hidden neurons, 4 hidden layers, so 10 to the 6 or 1 million parameters, a data set of 1 million data points. And we train for 10 to the 4 epochs. And that's kind of like the maximum amount of resources we invest into this. We use J nonlinearity, such size of 256, cosine annealing scalar, which was a bit problematic, but it gets the best performance. And then, just because we were using relatively wide, big models, changing a bit the weight initialization is good. Just that. So finally, the results. Here are the results. So you see the performance, the mean squared error of each training, and the scaling dimension. And in each plot, there are 3 different curves where we kind of also move in a secondary dimension. So here you see the scaling on dataset size for a network with 10 to the 4 parameters, 10 to the 5, and 10 to the 6 parameters. Here, the compute used for training with 10 to the 2 dataset size, 10 to the 4, and 10 to the 6, and so on. And here, the scaling in the number of parameters of the model. And the results are quite good. This is for the QQTTH. They're really good. You see very clear straight lines, clear plateaus. So here it's very clear that you are not constrained by the number of parameters of the model, but here you really are constrained by the dataset size. You can't really get any more performance from here. And in here below the plots, you see the fits for different power laws. So the fits are quite nice. So yeah, and they are very great results. And interestingly, the slopes, or the exponents of the power laws, are very consistent within each other, here and here, but not for the scaling in the number of parameters. We now understand why that's the case, and it's just because you really need to optimize the learning rate when you increase the size of the model. So we are working on fixing that, but the trainings take a lot of days, so we didn't have time to redo this plot. And also, if you pay attention, you will maybe see gray points in these plots. These are the actual results that we got, again, because in some cases, you really need to optimize the learning rate, but if we had, as you will see for many datasets, if we had to optimize the learning rate for each one of these cases and for all the datasets, we would have never finished. So we found something that works very much in general, but in some cases, okay, we see that here, we know that we can at least get the best previous results, so we kind of artificially flattened the curve. So yeah, that's why you see that. So moving on, I think I'm missing, here. And you could ask, is the scaling net independent of the shape of the network? Because as you may know, the number of parameters in an MLP scales roughly quadratically with the number of hidden neurons in the model and linearly with the number of hidden layers. So there are many possible combinations that get you the same number of parameters. And in one of the papers from the plot that I showed in the beginning for the large language modeling, they show that the results are independent of what they call the aspect ratio, so dividing the width, the depth by the width of the network. And but for us, that's clearly not the case. So here, as you can see, these are the best performances as a function of this aspect ratio. And the plot has a lot of information, but what's important is that the best and the worst performance for each one of these curves, which represents a fixed number of parameters, are at least an order of magnitude apart. So it's really not comparable. But we okay, so then how do we do the scaling? Because if it was independent of the aspect ratio, you can just increase the number of parameters as you wish without taking care as to how you do it. But here we doing this same plot, but using the number of hidden layers as the x-axis. We see, maybe by coincidence, that 4 layers seems to be a sweet spot for this process, so we decided to use that. But again, now that we know how to the problem I mentioned here about the slopes, and we now know how to fix this. This should also not be so much of a problem, but we didn't have time. So, well, moving on, I'm talking about the losses a little bit. Okay, so mean squared error, you already know that, but the heteroscedastic loss is this loss that allows us to get systematic uncertainties. And you get this loss by assuming that the amplitude regression follows a normal distribution, in the sense that the probability of predicting an amplitude A given a set of initial of momentum follows a distribution that has a mean and a standard deviation that you don't know. And then when you see a negative log likelihood, you try to minimize it, of course. So you minimize it, and you get this new loss that is just the negative log likelihood of a Gaussian. And you get these 2 terms, these extra new terms, with the uncertainty that kind of counteract each other, so you can still minimize the loss by making your prediction closer to the true value, but you also can minimize it by having this uncertainty be the correct calibrated one, because you don't want it to be too high, because if not, this blows up, and if it's too small, this blows up. So you really need the uncertainty to be well calibrated to your assumption. So then, okay, your neural network has 2 outputs, the amplitude and the uncertainty that you care about. And if this is well calibrated, this quantity, the pool, should follow a standard normal distribution, and it's a good test to check if your assumption is right and if everything is working fine. So then the results, very much the same. We see very clear scaling behaviors with very clear power loss. They are slightly worse for the heteroscedastic trained networks, but it's just because here we are showing the MSE, but we are trained on a different metric, so it makes sense that it's not as good. But yeah, I mean, again, basically the same, slightly worse. And here you see this weird behavior. This is again not well optimized the learning rates. We are working on fixing that. So, and just to show a bit more of the results, here is one example of the calibration of the pool that should follow a standard normal distribution in log scale, so that's why it looks like a parabola. And as you can see, it's in this example is very well calibrated. It has big tails, but that's usually the case. And we get very well calibrated uncertainties for every range we tested, except those 4 points that I showed that didn't have the learning rate well optimized. But yeah, and also we can see that the uncertainties go down. They become smaller as you scale up. So here you see that the uncertainties shift downwards as you increase the amount of compute, or as you increase the dataset size, or as you increase the number of parameters in the model. So again, very clear scaling behavior of the uncertainties as well. And just moving on more quickly, because I don't know how much time I have left. But here are more results trained just on MSE loss for the rest of the processes. And we can see, again, the very clear behaviors, clear straight lines, plateaus. Here is for the scaling on the computing resources. So you see, again, the bottleneck is very clear, the dataset size. And well, since we have the fits for all of these processes, we can test, and we know the dimensionality of each one of these processes. We can check, and we see this dashed line is the theoretical proposed relation between the exponent alpha and the degrees of freedom. We see some relation, I mean, big error bars, but there is clearly some decrease in improvement as your process becomes more complex, so higher degrees of freedom is this way on the plot, so as your process is more complex, you get smaller exponents of the law, of the scaling law, which makes sense. And again, we see that it breaks down for the WC process, but it makes sense. It's like a very pathological case with only 2 degrees of freedom. And we also see that the QQTTH is way off here. It scales very much better than any other process, and we don't really understand why. But we should look into that maybe. And yeah, and that's very nice results. And here, basically the same thing, but for the scaling on dataset size. Again, very clear scaling behavior, nice fits. Some of them are maybe a bit unstable, but okay, like in general, you see that it's very universal. And again, we have the fits, so we can do the same thing, and we see basically the same behavior, a bit off from the theoretically proposed behavior, but still it's very clear that simpler processes scale better and more complex processes scale a bit worse, but still you can get a very predictable scaling law. And okay, and just to finally mention the other model, the other net architecture, Alligator, which I don't have time to explain how it works in full, but basically it has permutation invariance and equivariance. So it performs much better than other alternatives when you have processes that allow permutation invariance of the particles in the process. So here, C plus 4 sheds. As you can see, for the same number of trained iterations, you see that it greatly outperforms by an order of magnitude the classical architecture you would use. And you see that there are some scaling behaviors here. These first numbers are this a weird behavior because of the batch size, and it's ignore this part of the plot. But from here onwards, there seems to be some scaling. But the thing is that we should continue this plot to the right, but the trainings take much longer. So like maybe a week or so. So it's we need to keep going, but it takes time. But it's very promising. So, well, just to finish, we observed very clean and predictable scaling laws for amplitude surrogates. We see scaling on all the 3 parameters that you can vary, the resources you can invest. We saw scaling with MSE laws and with the heteroscedastic laws, and we get well-calibrated uncertainties across many orders of magnitude and a good scaling behavior on the uncertainties as well, which is nice. We observed a relationship between the scaling and the degrees of freedom, which is also very interesting. And okay, we started looking into the scaling of this fancy architecture, but it takes time. So that's it.
Okay. Thanks a lot for the nice talk. We have questions.
Hi, thanks for your talk. I don't know if I misunderstood, but were you training your networks for 10,000 epochs each?
Yes.
With no early stopping?
Well, but because, I mean, early stopping, we save the best performant model.
Yeah, but
not, we don't stop.
I think you would not have to wait a week if you implemented early stopping and actually stopped it, because 10,000 epochs is kind of crazy.
What you see, I mean, let me show you. Like, here is, like, okay, 10 to the 6 iterations, which, I mean, if you translate it to epochs, it's roughly 10,000 epochs. And you see that in this case, it could reasonably keep going down. This is a not very well optimized learning rate, but because I don't have a plot of a proper training, but there are cases with this number of iterations that continue going down actually. So it's not, and the thing is that we want to really test how far we can push. So if by training for a week you get marginally best performance, that's what we want to see.
Yeah, I understand setting the limit high, but I don't understand why you should keep training, because then you might overtrain, right? And
yeah,
it can impact your results.
No, yeah, of course. But yeah, in the cases where we know that you're going to overtrain a lot, yes, we stop it.
Oh, you do?
Well, I mean, like for example, this one, the actual best performance was here, way back in the training, but so the result we show is this one, not this one. But in some cases where we already know that it's going to definitely overtrain, it was not obvious that was going to happen. We train for sure.
Okay.
But yeah, you have to kind of fine tune a little bit. But we don't waste resources.
And the learning rate too would impact, right? How long you have to train for.
Yes.
Yeah.
Yes, it is. It's,
Okay.
Any other questions?
It is actually a comment on behalf of people who do not use early stopping. Actually, it has become more and more common not to use early stopping and to keep training to the end, because early stopping has been proved to overfit the validation set, actually. So if you want to keep good generalization, both for industrial application but also scientific application, the best would probably be to go to the end, and actually 10,000 epochs, but well, it depends on the data set, but sometimes it's fine. It's perfectly fine to keep training for that long. For a large language model, it would be super weird, but depending on the data set, especially scientific data set, even 10,000 epochs, could be fine. It depends on the application, though.
No, it even depends here on which data set we are using. Like for some of them, you get the optimal performance way early, and you don't really need to train for that much long. But and also to add to that comment, I think it's been proven that if you are using early stopping to optimize for the validation loss, then kind of your validation set, which is usually small, becomes your training set, in the sense that you're optimizing for that. So then it's suboptimal, at least. So there are arguments to not use that.
I'll just take the moment because I just came to my mind. If you go back to this the learning rate plot that you just showed.
Yes.
Yeah. So here it seems like whatever, I mean, it has converged within, let's say, yard scale, something between 0.0 and 0.25. I think the best use of annealing, if you really want to do it, is to fix your period of this cosine function to be till this 0.25, and then use some kind of restart, maybe a warm restart with that periodicity.
Yes,
usually that, in case if it gets stuck in some local minima which you are trying to cure, this could be a way to go about it.
Yeah, we well, not with these data sets, but I've experimented with that before. It works, but sometimes it goes doesn't really work that much. But the problem with that is that you need to know beforehand, or you need to do this at least once to know where to optimize the learning rate or the scheduler period. So, and for 1,000 different runs that we needed to do, that's not really possible.
Probably you run for a little bit because you see it converges. That gives you a rough idea, and then maybe.
No, I mean, of course, there are a lot of places where you can optimize it a bit more, but this, in general, it works surprisingly well for for everything we did. So, except for a few cases, but yeah.
Great. Yeah. Sorry, I got greedy.
It's just a small comment on the comment. I think you can kind of, in principle, you could basically avoid this overfitting on the validation set if you do some kind of k-fold cross-validation, right?
Yeah, of course.
And this is a way that you are definitely not wasting resources because you're not training extra epochs after the validation loss didn't improve for a while. So, I mean, this seems like I don't know, just a comment.
Yeah, I mean, in practice, the way this was made was setting everything to run and going to sleep, and next morning seeing what happened. So it's not like I could stop it in the middle if I see it overshooting, but
you don't have to look at it to see that. You can just, like, after 10 epochs, it doesn't change.
No, yes, but then the thing is that and this is actually the main problem I had, is that the patients you choose really constrains you in the sense that, okay, for example, here, in this case, it wasn't the case, but for example, if you chose a patient that is smaller than, I don't know, this small range, you would have been stuck there, and maybe you could have gone further. And the problem is that patients, the optimal patients you should choose, changes as you scale everything. So then it's kind of like you need to optimize the patients.
You have to make concessions, right? So I guess you have to choose the patients that make sense for you. If you're doing a small test, you can do patients of 10. If you're doing that for 10,000 epochs, you can.
No, I agree that in the,
Question for you. Like, what was the learning rate on this curve, if you remember?
it's up there. So. No, but yeah, I mean, I agree that in practice you would never do this, but if there is a chance that if you kept training for 1 million epochs more, you would get a bit better performance. That's what we are trying to check. So, of course, in practice it would be, like, you could stay here. Like, nobody would do this in practice because you can be satisfied with the marginally worse performance but training for 1 hour instead of 3 days. But yeah, I mean, it's I agree completely.
Thank you for the presentation. I just have a quick question. At some point in your talks, you mentioned universality, and we see power laws everywhere. But is there an underlying, understood theoretical reason of why this power laws appears? Is like, can we do some universality class, some normalization group procedure, things like that, or do we know why this power law appears?
As I mentioned, there are. It's not fully explained at all. There are some, I think there is a paper that let me go back. This paper that I reference here, they do some theoretical explanation as to why you would expect this gradient descent on the loss landscape to depend on the dimensionality of the data and on the dimensionality of the manifold of the representation, the internal representation that the network does. So that's why it's applicable even for large language modeling, where you don't have a definite dimensionality, but your network does something with the data and puts all your data in some kind of manifold, and that the dimensionality of that manifold is somewhat related, or for their explanation, it should be related to the scaling behavior that you see. But it's not, there is nothing very developed as far as I know, at least. But yeah, I mean, it's a bit, empirically we see it, and again, here we with processes where we definitely know the dimensionality of our dataset, theoretically. It's not only a toy dataset as people do in this paper that they tested for toy datasets, but here it's like real physical data. And we see it as well. We see a relation, at least. We don't see that relation, but so it seems to be true mostly, but it's not fully explained.
Yeah, because precisely it's striking that it works for very different kinds of models and also on real data, and we still see these scaling laws everywhere.
No, yeah, like it's. I have sometimes when I'm showering, I have an idea like it would be really cool to have another branch of my PhD and focus on that. But yeah, I mean, someone has to explain it at some point. But it's.
Thank you.
Any other questions? No? I will wander later. We move on to the next one. Thanks a lot. Let's thank Joaquin again.